All right, so yesterday we talked about ring opening epoxides, and we said if you're under non-acidic conditions, that means your nucleophile is most likely going to have a negative charge, right? If it were under acidic conditions, it would be protonated. You'd have neutral molecules acting as your nucleophile. And we said under non-acidic conditions, meaning basic conditions, that your nucleophile will always, always, always add to the less substituted side of your epoxide, right? So that red carbon is the less substituted side. So in all of these cases, the nucleophile added into the less substituted side. We said you could use sulfur nucleophiles, carbon nucleophiles, so cyanide can add in. You can use oxygen nucleophiles and get an ether installed. You can also use a carbon nucleophile as a Grignard reagent, add that in, or you can do lithium aluminum hydride and add a hydride into the less substituted side. So it's a pretty useful trick we have anytime we make an epoxide is we can ring open it and functionalize the carbon next door to that alcohol. All right, so this was one important half, was the non-acidic conditions. However, we said we get completely different reactivity when we're dealing with acidic conditions. So what I'm going to do is kind of cut this in half down here with a green line. And then below it, we'll do acidic conditions. All right, so same epoxide we're starting with. Let's think about how we can functionalize it to get some different functional groups. So for this one, I'm going to try to get an anti-diol. What sort of reagents would I need to get an anti-diol? Not quite. We've already made our epoxide, right? So this epoxide is our assumed starting material for all of these. So how can we go from our epoxide to an anti-diol? Yeah, H3O plus, right? We've already formed our epoxide. All we need to do is add in acid and water. So most people would just say add in H3O plus. And when you do this, right, this water, will it add to the more or less substituted side? It'll add to the more substituted side, because if you remember yesterday, I said if you do have a tertiary carbon, meaning this carbon, under acidic conditions, your nucleophile will actually prefer to add to the more substituted side. It's kind of this weird, unusual behavior due to electronics. So in this case, the water that was added in added to the more substituted carbon, and it's on that lower side as I have it drawn. All right, let's think about a slightly different one. What if I want to add in some sort of thiol? So in this case, it's a thioether, so sulfur in between two carbons. What reagents do you think I would need? It's really similar to this one that we did up here, but do you notice the sulfur is coming off the more substituted carbon now? Up there we use a sodium salt, and this one we can't because it's under acidic conditions. So we do need some sort of acid for sure. So I'll just write H plus, and then what do you think the other reagent will be? Yeah, just something with sulfur that's neutral, right? So I write HSR, so it'd be some sort of thiol, and you can actually get it to add in. So like I said, you need to have acidic conditions, and then your sulfur will add to the less or the more substituted side. All right, along those same lines, what if you want to make a normal ether? What sort of reagent should we use? It looks pretty similar, right? We need some sort of acid. And then what will the next step be? An alcohol, right? So I'll just write generic alcohol. All right, and then last but not least, what do you think happens if you treat this with some sort of halo acid, let's say HBr? What do you guys think will add to the more substituted side? Yeah, exactly, the halogen, right? because the proton on there is going to act as your acid source. The conjugate base could be your nucleophile. So then you can end up with your halogen coming off of your more substituted carbon, and you can get an halogen installed there. The only one that, like I said, doesn't behave like the normal halo acids is hydrofluoric acid, so that one's not typically seen. So then sometimes people will ask me, all right, if that's the case, if we can throw in some sort of halo acid and get the conjugate base to add as a nucleophile, what sort of acid do we want in these situations? We do need to be very careful with the acids that we choose. We want the conjugate base to be non-nucleophilic. So I'm going to go ahead and put a little asterisk here. And I'll say it's usually H2SO4, H3PO4, or tosylic acid, which is abbreviated TSOH. And the reason that those acids are used is their conjugate bases are really, really crummy nucleophiles, and they won't ring open an epoxide. So you do have to be careful. You can't just throw HCl in, otherwise you'll actually get a halogen acting as your nucleophile. Does that make sense? All right, so let's take a look at some practice problems, and then we'll work through these. Whoop. All right, so practice problems. What I'm going to do is give you a set of reagents, and I want you to help me determine what product or products will get out, and pay attention to not only regiochemistry but stereochemistry as well. So step one in this reaction is MCPBA. Try to show that intermediate after you react it with MCPBA. And then step two, what I'm going to do is treat this with catalytic acid, meaning sulfuric acid, phosphoric acid, tosylic acid, and methanol. So let's try to figure out what this would be. I'll give you guys a simple trick you can use too. Abbreviate this as a pH or a phenyl group. It'll be a lot easier to write things out without having to draw the full ring. So what do we make with MCPBA? An epoxide. All right, so like I said, I like to just draw my parent epoxide, and then we know each corner can have a dash and a wedge, and then we've got to fill in what's coming off of each dash and each wedge. Give me a thumbs up if you think you got the epoxide. All right, so let's try to do this as a group. All right, I'm just going to put a methyl group on one of these because we know we've got a methyl group coming off both sides. So I'll say, all right, Me here. Where should the other methyl group be? It's got to be on this side over here, but will it be a dash or a wedge? A wedge, right? Because we know the methyl groups have to be on the same face because they were on the same face of the alkene to begin with. All right? All right, and then let's say this carbon over here has to have a phenyl group, so I'll just say, all right, the phenyl group's got to be here, so I'll just abbreviate that pH, which means on the other side, for the dash position, we must have what? A hydrogen, that's assumed. So I'll draw that in. Do we have to worry about enantiomers here? Do we have stereocenters? Yeah, absolutely. We do have stereocenters, so because of that, we will end up with the mixture of enantiomers. Like I said yesterday, the only way to not get enantiomers really is to do the sharpless epoxidation or just have no stereocenters to begin with, right? So we do end up with the mixture of enantiomers. Then step 2, we're going to treat this with catalytic acid, which means we're going to protonate this epoxide. And then I still have this phenyl group right here. And then in this step 2, we also have methanol floating around. My homie here. Which carbon is it going to add into? The left carbon on the epoxide or the right carbon? Yeah, the first thing you always got to do is check if you have any tertiary carbons, right? Do we? Yeah, absolutely. We'd say we have a tertiary carbon. If we've got a tertiary carbon and we're under acidic conditions, that's the one to be attacked. If we're under basic conditions, we don't care. We always go after the less substituted side. Okay, so in our next step, this is going to attack in and slingshot this open, right? So now what we need to do is draw our next intermediate over here, but pay particular attention to stereochemistry. I'll also write plus En here. If you think you got it, give me a thumbs up. A few thumbs. Oop. One very important thing to remember with these reactions too is that they're SN2 reactions, right? So the carbon that you attack is going to get flipped inside out like an umbrella. It's going to undergo that inversion that we saw last term. The carbon on the right, the unattacked one, is going to stay exactly as is, right? The stereochemistry is not going to change. It's just going to be static. All right, so the carbon on the right, we know when it slingshots open, we'll have an alcohol up here. The methyl group, if it was untouched, will still be a wedge. The hydrogen will still be a dash because we didn't touch that stereocenter at all. On the other side, the methyl group is actually going to get flipped up, kind of like an umbrella flipping inside out. It's still going to be a wedge. So I'll write Me. Our phenyl group will be a dash. And then down here, at the attacked side, we're going to have this methyl group coming off the oxygen. And then what do you think is going to happen in our last step? Yeah, deprotonate it, so I'll write minus H plus. And it's important to remember in both of these situations, we will have an enantiomer that's a mirror image. So our final product for this reaction will have an ether coming off the more substituted carbon, an alcohol off the less substituted carbon. And then we also need to pay attention to the stereochemistry, like I said, because we're inverting one of these stereocenters. Does that make sense? I did. It's a little bit weird to see, but in this case, we flipped it up. You see how the methyl group was pointed down as a wedge, and we inverted it by flipping it up, kind of like an umbrella flipping inside out. So that is an inversion. I know we got kind of used to always flipping dashes to wedges and vice versa. You don't have to do that, right? You can show an inversion as an umbrella flip sort of thing. So this is more an example of the umbrella flip. All right, let's try another one and see if you guys can do this on your own. All right, so for this one, I've got an alkene with an isopropyl group and an ethyl group down here. This is going to be a bit steppier. So step 1, MCPBA. Step 2, phenyl magnesium bromide. And then step 3, we're going to treat it with dilute aqueous acid, so H0+. I'll get us started with kind of the same skeleton that we had before. We know step 1 we're going to make an epoxide, but we need to fill in our substituents. And then step 2, we're going to treat this with phenyl magnesium bromide. And like I said, a phenyl group is basically a benzene ring attached to something else. In this case, it's got a negative charge on one of the carbons. And then the magnesium bromide countercation, right? So now what we need to do is determine what the heck goes on each of these legs of our epoxide. Who thinks they got that far? Most people? All right, let's start on the left carbon, and we'll try to keep it the same left carbon to left carbon, right? All right, so I'm going to pick one of these over here. So for example, I'd say, all right, this group right here is an ethyl group. So I'd say, all right, we've got an ethyl group coming off that left carbon. That means this back here must be a methyl group, so I'll just say Me. All right, what must be on the wedge next to the ethyl group? Hydrogen, all right, so I'll go ahead and fill that in. It's our assumed hydrogen. And then in the back, what would we call this group? Isopropyl, so I'll abbreviate that IPR. And like I said, we can do methyls as Me. So I'll say IPR. Do we have to worry about enantiomers here? Do we have stereocenters? Yeah, absolutely. So I'll write plus En. All right. If we look at this now, we've got to determine, all right, are we going to go after the more substituted carbon or the less substituted carbon? What do you guys think? Less substituted, right? Grignards are really, really strong bases, so this is not under acidic conditions. Okay, so the less substituted carbon we know has to be this side because it's a secondary carbon, not a tertiary carbon. So then we'd say, all right, this Grignard can act as a very strong nucleophile, attack that, pick up electrons, and now we need to include our product with the correct stereochemistry. So if we're slingshotting that open, the oxygen's going to be up here. The phenyl group that we added on is going to be down here. I'm just going to abbreviate that as pH. And then we've got dashes and wedges here and here. And this oxygen, when we slingshot it open, has a negative charge. All right, so let's focus on these groups over here. What is going to be the wedge? It's got to be the hydrogen, right? We're flipping these up, essentially. So the two legs are getting kicked up into the up position. So the hydrogen's still going to be a wedge. The isopropyl will be here. And then the next one we've got to do is determine what's coming off these. So what's going to be the wedge there? The ethyl. Absolutely. We're not changing anything there. And that means the methyl group must be here. And we'd also have an enantiomer. All right. Last but not least, I said we would have aqueous acid, which is really just a source of protons. Whoop. So I'll just write plus H plus. We know this oxygen is going to steal a proton, and we'll end up with our neutral molecule, where the phenyl group is anti to the alcohol. And we have our correct stereochemistry. Whoops, it should be a methyl group. Plus our enantiomer. And there we go. So there is a lot to pay attention to. This is one of the more complicated reactions that we've seen. So I would recommend practicing this, not only to practice which carbon is more likely to get attacked, but make sure you're getting the correct stereochemistry where necessary. You guys want to try a challenging one? All right. So this one's more synthesis based. We're going to start out with an alkyne, a terminal alkyne, so it's got a proton coming off of it. And our goal is to use whatever reagents necessary to make this alcohol. So 1, 2, 3, 4. Looks like this. This gets tricky, but I will give you a hint. You have to use an epoxide for this, or at least it's better to use an epoxide. I'll give you guys a hint too. If we look at our starting material versus our product, looks like we've gained carbons, right? We only know 2 ways of gaining carbons, or at least 2 main ways of gaining carbons. One was deprotonate your alkyne and do SN2 alkylation, right? The other one was Grignard chemistry, right? So make it into a Grignard. Question is, which one do you think we're more likely going to be doing here, based on our last example? Make it into a Grignard. So the question is, all right, how can we turn our starting material into a Grignard? And if we think about it, right, this had all of these carbons, which means it's going to end up here. And then ultimately, we need to add on the rest of this as a separate chunk. Make sense so far? So how do we make this green circle into a Grignard, starting from our starting material? So I'll give you guys a minute to think about that and then check with your neighbor. If you want, you can even work backwards kind of and say, all right, let's focus on what this green section would have been. What would that have looked like if it were a Grignard reagent? Well, we'd say, all right, this carbon right here is the sticky piece that added on to something new. So what should be attached there as a Grignard reagent? Yeah, MGBR. Okay, so then the question is, all right, we need to make this Grignard reagent. That's our goal. All right? How do we make Grignard reagents? We can't just throw in MGBR at it and have it work, right? What's our starting material and reagent necessary to make a Grignard? We need an alkyl halide, right? So something without the magnesium that looks exactly like it. So we'd say, all right, our Grignard reagent must have looked like this. And how do we get the magnesium to insert? Do what? Ether and just magnesium metal, right? So magnesium metal and ether solvent. So I'll just write ROR as our ether solvent. Okay, that works. And now the question is, all right, how do we get from there to there? We can't do it in one shot, that's for sure. Okay, so you're proposing maybe make our alkyne into an alkene and then add in our bromine? I agree with that. So in this one, I heard H2 and Lindlers. All right, when you do that, you'll convert this starting material into an alkene. And then how do we get the bromine to get installed on the less substituted side? Yep, HBr and peroxide. That does anti-Markovnikov halogenation, and like we said, then throw in magnesium and you've made yourself a Grignard reagent. All right, so now when we're looking at this, the question is, what reagent do we need to install that blue chunk? We need an epoxide. That was in my original hint. All right, does it need to be a functionalized epoxide or just a plain epoxide? To me, I'm just seeing 2 carbons attached, nothing else fancy. So in our last step, what we're going to do is treat this with the simplest of all epoxides. This is called ethylene oxide, right? Which makes sense because we know this carbon will attack this, slingshot it open, and then the alcohol will be off your less substituted carbon. Makes sense. All right, what do we need as step 2 to ensure that we're getting a neutral molecule? Water or some sort of dilute acid, doesn't really matter, but that whole blue section was actually added on by using our ethylene oxide unit. I will show you a simple trick. If you notice that you're adding 2 carbons on, and your alcohol is coming off the less substituted side, that's a good sign that you're making some sort of epoxide or using an epoxide, right? What about if your alcohol is on the more substituted carbon? We can't do that very easily with epoxides. We can do that with Grignards and ketones and aldehydes, though. So they are closely related reactions. In particular, what I highly, highly, highly recommend that you all do is go to the end of the chapter where it talks about synthesis strategies, and it will run through a bunch of practice problems distinguishing when should I use when should I use epoxides and when should I use granular reagents with ketones and aldehydes. It's a good study aid. So I really, really recommend the synthesis problems. All right, so let's take a look at thiols as the last section for this chapter. And thiols are very similar to alcohols. They're the sulfur analogs of alcohols. Why do you think they behave so similarly? Yeah, they're in the same column, right? We know with periodic trends, if you're in the same column, you have similar reactivity. Therefore, thiols behave somewhat in the same manner as alcohols. The difference is two things. One is they stink to high heaven. Two is sulfur is massive compared to oxygen, and we saw last term that that means it's a really good nucleophile. All right, so let's take a look at naming. They actually add sulfur-containing compounds to natural gas, which is why you can smell natural gas. Normal natural gas you can't smell, which could be a bad thing. You want to know when there's a leak. But that kind of gets to its stinkiness. All right, so let's name this alcohol first. And then we'll do the analogous thiol over here. So what would the alcohol on the left be named? And then check with your neighbor. Thumbs up if you agree with your neighbor. All right, so longest continuous carbon chain that contains your alcohol would be how many carbons long? 4. And then do we want a number going left to right or right to left? We want to go right to left because we want the alcohol to be at the lowest position. So we've got a longest carbon chain, alcohol off of carbon 1, methyl group off of carbon 3. So this would be 3-methyl, 1-butanol. Make sense? All right, so then the question is, well, how does this differ whenever you have a thiol? The prefix is entirely the same. So I'd say 3-methyl, 1-but, and thiol. So really the big difference here is we change the OL to an E with a thiol behind it. It's actually a pretty simple naming convention for simple alcohols. Does that make sense? All right, there's a lot of alcohol. Yep.
Do you have to include the 1? It's not assumed?
It's not assumed here because it could be coming off of carbon 2, for example, so you do want to indicate which number it's coming off of if it's not clear. Yeah. All right, so let's do the next one where we get into more complicated thiols. And this is what you do when you have multiple functional groups. So I'll call them FGs for functional groups. And we have to actually use a different naming convention here. Because in this situation, thiols are lower priority than the alcohol, so we can't have them as a part of the suffix, right? We actually would need to treat this as some sort of substituent coming off the parent chain. Just like before, we know our longest carbon chain. B3, 4. We know we've got a methyl group here. And then over here, we've got this SH group. This is called a mercapto group. All right, so if we go ahead and we name this, this would be 3 mercapto, 3 methyl, 1 butanol. This mercapto is basically a placeholder for the SH group coming off. The reason we do this is it depends which functional group has the most important priority, right? Alcohol in this case outranks the thiol, so we treat the thiol as a substituent, not a part of the parent. Make sense? So if you hear mercapto, it sounds weird, but you should think thiol. It's got some sort of SH on there. Okay, so let's take a look at preparation of thiols. Luckily, this is really straightforward. What reagents do I need in order to accomplish this transformation? This is something I could have put on your exam last term. What's that? Silence. This is SN2 chemistry, right? We've got a good leaving group. We're trying to swap it out for an SH. Do you think it's SN1 or SN2? SN2, right? Because our electrophile is primary, so I'd say SN2. Do we need a strong nucleophile or a weak nucleophile? Strong. So it should have a negative charge, ideally. That means this SH should be negative. And oftentimes, you show the countercation, so this would be NaSH. Oftentimes, people just call this NaSH. So you can actually add this in as a salt. It'll do SN2 chemistry. We're familiar with that. Backside attack, kick off our bromine, and we end up with our thiol. This also works pretty well for other electrophiles. So the question is, all right, here, what reagent do you think we'd need? And do you think it's SN1 or SN2 based on the reaction? It's got to be SN2, right? Because we inverted that stereocenter. Again, that means we need a strong nucleophile. And so I'd say NaSH. However, last term I told you that SN2 chemistry normally doesn't work very well on secondary carbons. It's too hindered. Why is it allowable here? Last term we saw a lot of SN2, E2 combos, right? With secondary carbons. Why don't we have E2 here? Yeah, it's sulfur. Sulfur's not a good base. That's really what it boils down to. Is this is not a good base. Which means E2 doesn't occur. If we did the same thing with hydroxide, with OH negative, then E2 would actually be major and we'd get very little SN2. But sulfur, we know, can only do SN2. It doesn't do E2. All right, so that's typically how you make thiols. Let's take a look at the relatives of thiols, disulfides. All right, disulfides are really big in biochemistry, primarily due to one specific amino acid that has a thiol functional group. Does anybody know the amino acid that has a thiol on it? Cysteine, exactly. So cysteine is an essential amino acid. It's incorporated into the backbone of proteins, right? And so if you have two cysteine residues next door to one another, meaning in close proximity, they'll actually react with one another to form what's called a disulfide. And all that is a sulfur-sulfur bond. This is hugely important in biochemistry. This disulfide linkage actually provides structural support for proteins and can change the behavior of enzymes. So it is something that's strictly controlled within your body. In a lab, we can do this synthetically, though, and the reagents that are needed are sodium hydroxide, water, and bromine. At least that's the one our book shows. In reality, there's a lot of different reaction conditions that will work. All right, do you think this was an oxidation or a reduction reaction? Think about the sulfur, right? Is it gaining or losing electrons in this reaction? It's losing one, right? If we think about sulfur, sulfur is more electronegative than hydrogen, so it's getting both those electrons. Whereas in the disulfide, it has to share it with the adjacent one, so it's losing an electron. So this is an oxidation reaction. The cool thing is this is somewhat reversible. And if we want, we can actually snip this back apart into individual thiols, and we can do this using hydrochloric acid and zinc, and this is our reduction. And it's important to remember this sulfur-sulfur bond is the disulfide. One interesting thing, if you've taken microbiology and classes like that, is if you've covered thermophiles. Thermophiles are bacteria that can survive at really, really high temperatures. Thermophiles, in order to handle those high temperatures, have a lot of disulfide linkages. That way their proteins don't denature as easily. So it actually provides a lot of structural support for those proteins. All right, last but not least, we've got sulfides, which are similar. And you can oxidize a sulfide to, so let me write this down, sulfide to a sulfoxide, where it has an oxygen double bond to the sulfur. It still has a lone pair on the sulfur. Sulfur is kind of weird. It doesn't like to follow the octet rule as much as carbon. And then last but not least, we can oxidize this even more because sulfur is unique to a sulfone. So this is an oxidation, and this is our second oxidation step. The first one, we have to use a very specific reagent, sodium periodate, NiO4. And that will stop at the sulfoxides. Similar to oxidation chemistry we saw last term, gentle oxidizers will stop there. If we want to overshoot and go all the way to the sulfone, we just pull out the big guns and we say, all right, we're going to oxidize you with pure hydrogen peroxide. Alternatively, like I said, you can just jump that intermediate and use hydrogen peroxide and go all the way to the sulfone that way. Make sense? People will ask me too, do we need to know these mechanisms? No, they're a little complicated. Honestly, we're not going to get too much into sulfur chemistry as far as synthesis goes, but I do show it to you, especially this one, because it shows up a lot in biochemistry. Like I said, it's very important to understand. All right, so let's take a look at the summary of reactions really quickly. We covered preparation of ethers, and we said that's just fancy SN2 chemistry called the Williamson ether synthesis, where you deprotonate an alcohol and react it with an alkyl halide. We said you can do alkoxymercuration, where instead of adding water in the first step, you add in an alcohol, and that will give you an ether. Pretty easy. And then we said with ethers, you can treat it with super duper strong acids, so HBr, HI, and cleave the ether into two alkyl halides. Or you can do the same thing with aromatic ethers as well. I skipped the full auto oxidation section just because it's a little bit confusing and not synthetically useful. And then we talked about preparing epoxides either by using MCPBA or doing the halohydrin reaction followed by the intermolecular SN2. The other thing we went over was the chemistry of ring opening epoxides. So this is similar to the reaction map we previously made. And then we went over the thiols and sulfides. The thiols and sulfides, don't worry about too much. I want you guys to focus primarily on the epoxides and reactions of ethers. Make sense? All right, so I think we'll take a short break. If you do want to hang around for the study session, we can start working on synthesis problems, and you guys are welcome to push tables together too.